Let's talk about the invisible force that powers pretty much everything around us. I'm talking about the energy that's locked away inside chemical reactions, from the cozy warmth of a campfire to the massive machinery that runs our industries. But here's a question for you. Why does a bonfire feel so warm, right? But an instant cold pack does the exact opposite. It gets freezing cold. They're both just chemical reactions, so what's the deal? Well, the answer, as you're about to see, is all about how they manage their energy. All right, so here are the official terms. A fire is what we call an exothermic reaction. The easy way to remember this is that the heat exits the reaction. It releases energy. The cold pack, on the other hand, is endothermic. It actually pulls heat in from its surroundings, which is why it feels so cold to the touch. So the real secret here is this constant tug of war happening at the molecular level. You see, to start any reaction, you have to spend some energy to break old chemical bonds. But then, when new bonds form, energy gets released. The whole game is about which number is bigger. If you get way more energy back than you put in, well, that's your exothermic bonfire. Okay, so how do scientists and engineers actually keep track of all this? You can't just say a reaction is kind of hot. You need precise numbers to build anything useful. You need an energy scorecard. And that scorecard has a name. Enthalpy. You'll see it written as delta H. Honestly, the best way to think about it is like an energy bank account for the reaction. Is it making a withdrawal from the environment's heat, or is it making a big deposit? And the best part is the accounting is super simple. If that enthalpy value is negative, it means the reaction's bank account went down because it gave away energy as heat. That's exothermic. If the number is positive, it means the reaction took in heat from the outside world, so its balance went up. That's endothermic. That little plus or minus sign tells you the whole story. Now, as you can probably imagine, it's impossible to go around measuring every single chemical reaction in the universe. So engineers, being the clever people they are, came up with some amazing shortcuts to figure out the energy of a reaction without ever having to actually do it. The first big shortcut is called the heat of formation. Think of it like this. Every chemical compound has a standard energy price tag that tells you how much energy it costs to build it from scratch, from its most basic elements. So if you know the cost of all your ingredients and the cost of your final products, you can just do the math to find the total energy change for your whole recipe. Shortcut number 2 is the heat of combustion. Now, this one is absolutely massive for anything related to energy. It's a direct measurement of the total heat you get when you completely burn something. For any kind of fuel, this number tells you exactly how much bang you're going to get for your buck. But the ultimate shortcut, the real game changer, is something called Hess's Law. This is just brilliant. It says that if you have a tricky reaction you want to figure out, you can treat other simpler reactions like puzzle pieces. You can add them, subtract them, even flip them around. And as long as they add up to your target reaction, you can just add and subtract their energies to get your final answer. It's like chemical algebra. All right, that's enough theory. How does any of this stuff actually work in the real world? Let's take these ideas and apply them to a practical problem, figuring out just how much power an industrial furnace is kicking out. So here's our setup. We've got a furnace, and it's burning 100 moles of propane gas every single second. We know exactly what's going in, the fuel and the air, and we know exactly what's coming out, the exhaust. The big question is, how much heat is this thing actually generating? Thanks to those shortcuts we just talked about, an engineer can calculate that exactly. And when you run the numbers, using those heats of formation we talked about, you get the answer. The furnace is releasing 126 million joules of energy every single second. That's a power output of negative 126 megawatts. And notice that negative sign? Yep, that tells us it's a massively exothermic reaction, just as we'd expect. To put that number into perspective for you, 126 megawatts is an incredible amount of power. It's enough to supply electricity to a small city, to over 100,000 homes. This is exactly why getting these calculations right is so incredibly important. And look, this isn't just about giant industrial furnaces. This idea of understanding and controlling the energy and chemical reactions is, well, it's fundamental to basically everything in our modern world, right down to the tiny little reactions happening in our own cells. I mean, think about it. Designing better fuels for our cars, creating the batteries that power our entire digital lives, inventing new medicines, heck, even just understanding how our bodies turn a sandwich into energy, it all comes down to managing these exact same principles. It really is the hidden engine driving our world. This quote really nails why this is so important from an engineering perspective. It's all about control. If you know the energy balance, you know exactly how much you need to heat something up or cool it down to keep it running safely and efficiently. It's the key to making everything work on a massive scale without things, going wrong. And that kind of leaves us with one big final thought. Human history has really been defined by the reactions we've learned to control, from fire to steam to nuclear fission. So as we look ahead and we face these huge challenges like climate change, the real question is, what are the next reactions we're going to master? Which ones will power our future?